All right, so I'm going to talk about measuring the CMB on small angular scales and what you can learn, additional information you can learn from that in regards to inflation and other new physics. And unfortunately, I did add in some slides just in case there were technical difficulties with Bill. So I might repeat some of the information, but I'll go fast over that, as Bill described. And this is showing some of the sort of the current relevant experiments for small scale CMB anisotropy. SPT up here, Atacama Cosmology Telescope, of course Planck, and then polar bear. All right. So, you can think of the universe as a high energy physics lab, and as you go back further in time, you're probing higher and higher energies. And we suppose that inflation happened at this very early time, fractions of a second after the Big Bang, sort of at the gut energy scale, where the universe underwent this period of exponential inflation. And so in principle, if we can look back, we can get this insight in this very high energy physics that was really unattainable by any other means. But as you go forward in time, there's more physics accessible in the early universe, and eventually, at later times, when the universe is only about 1 second, the universe becomes transparent to neutrinos. And so in principle, you can get information about this cosmic neutrino background, learn about neutrinos themselves, which is the neutrino analog of the cosmic microwave background, which was emitted around 400,000 years after the Big Bang, when the universe is much cooler, around 3 Kelvin. So the CMB gives us remarkable window into this early universe. By those signatures from early physics can leave imprints in the CMB itself, which we measure from redshift 1100. But in addition, the CMB has had to travel across the entire observable universe to get to us, and over this 14 billion year journey, it can be imprinted with signatures of structure formation and other physics, which can tell us things about structure formation, lensing from large scale structure, reionization, and later on the formation of clusters of galaxies. And so I'm going to give you a little sense of what additional information you can learn from that. So, of course, we typically characterize the information in the CMB into this power spectrum, which on large angular scales is dominated by the power from the initial conditions and the integrated Sachs-Wolf effect, power from large-scale structure. But of course, you see this, by the time you get to degree angular scales, you see this typical acoustic oscillations that are generated from gravitational instabilities in this primordial plasma. And this tells you a lot of information about not only the geometry of the universe, but the contents by measuring the heights of these acoustic peaks. And then at smaller scales, you can learn more about the expansion of the universe and also the relativistic energy density of the universe, which I'll talk more about. And this is the picture today where we have this extremely precise measurement of the CMB temperature power spectrum. We're now, when you combine the latest measurements from Planck, WMAP, ACTS, SPT, you can see that we're measuring 9 acoustic peaks in this primordial CMB temperature power spectrum. And if you fit a lambda CDM model to this, just a 6-parameter lambda CDM model, it fits extremely well over this entire angular range. And this is where we get these, from CMB alone, we get very precise constraints in both the matter, the baryon, and matter density. And this is something that Mike Turner brought up earlier this week, how there's this 40 sigma offset between the baryon fraction and the matter fraction inferred from the CMB power spectrum measurements. So this is a slide that Bill also showed. So currently right now, to get after inflation and energy scale inflation, we're trying to measure this tensor to scalar ratio R. And currently the CMB temperature measurements have effectively bottomed out on what they can do on their constraints in R from just cosmic variance, because most of the impact of inflation on the temperature power spectrum are at large angular scales where your cosmic variance limited. So basically the best limit now on R is around 0.10 at 95% confidence, and we're not going to do any better from temperature. So the only place we can go to improve measurements is for polarization. Another interesting piece of physics is you can actually indirectly measure this cosmic neutrino background through measuring the different angular scales in the CMB. So there are 2 relevant scales, the sound scale, which is basically the time a sound wave could travel in the universe at the time of recombination, and then the damping scale, which is related to the Silk damping scale, how long, just the relative thickness of the CMB at the time of the surface of last scattering. And these scales depend differently on the Hubble constant. So by combining them, you can get a measure of what the Hubble constant was at the surface of last scattering, which gives you an ability to effectively measure the relativistic energy density of the universe at that time. And since at recombination, the universe was about 13% neutrinos by energy density, you can learn in principle a lot about the neutrino sector. And this is showing now the Planck constraints. We typically characterize that constraints to this NF parameter, which is the effective number of relative species, which we expect to be 3 from just 3 neutrino species, and there's a small correction to that from extra energy or entropy injection in the early universe from matter-antimatter annihilation. You can measure that NF variable parameter, and also neutrino mass, which comes in through the integrated Sachs-Wolf effects at early times, and also detection of gravitational lensing. And you can measure those with pretty impressive precision already today. We can constrain this NF parameter to be 3.3 plus or minus 0.3. So already we have this corresponds to a 10 sigma detection of this cosmic neutrino background at the time of recombination. And this measurement of the neutrino mass is basically bottomed out from the integrated Sachs-Wolf effect, so the only way to improve it further is improvements on measuring this gravitational lensing. So the CMB is a really unique tool for lensing because it's the largest redshift source in the universe. It's from redshift 1100, and its source redshift is known. So it allows you to probe really high redshift structure formation in the universe in a unique way. And as the CMB photons traverse this 14 billion universe over 14 billion years, on average, they're reflected by about 2.5 arc minutes from just gravitational lensing from large-scale structure. And the peak in the efficiency of this lensing happens about midway to the CMB, which happens around redshift 2, corresponding to something like 7,000 megaparsec scales. And these deflections are coherent on degree angular scales. So lensing creates sort of small-scale wiggles in the CMB that are correlated on degree angular scales. And we can look for that signature to measure lensing. And I don't want to go too much into this equation, but basically this angular deflection of the CMB photons are dependent on this integral over a co-moving distance, which depends on both a geometric distance terms related to the source redshift and the lens redshift, and then also the gravitational potential of the universe. So by measuring this term, you're both getting information on the geometry of the universe and also the growth of structure, particularly at late times, around redshift that impacts structure growth at redshift 2. So this gives you most sensitivity is that for late-term parameters that affect that, such as W, neutrino mass, and curvature. So this is showing now the best measurement today of the CMB lensing power spectrum. So this is the CL55. This is a measurement of the lensing potential power spectrum from Planck. So only recently was gravitational lensing detected in the CMB. At something like, in 2011, it was detected by 4 sigma by ACT, followed up soon after with the 6 sigma detection by SPT. And then now the best detection of CMB lensing is 25 sigma by Planck. And that's what this is showing here, the Planck data points. And at this level of detection significance is interesting because this effectively gives you a 4% constraint on the normalization of this lensing power spectrum. And 100 MeV neutrino mass shifts the normalization of this curve by about 5%. So you're starting to get sort of at that level of precision where you can constrain neutrino mass at that level. And what experiments like SPT or ACT or Polar Bear do, well, better than Planck is they typically observe obviously smaller regions of sky, but deeper. And this allows you to recover the CMB lensing power spectrum at just finer angular scales. And basically the SPT sensitivity improves on Planck measurements around L of 500 right now. And one big future application of this is that it allows you to actually now make a map of the matter distribution of the universe, where this is now showing the SPT-SE 2500 square degree lensing map, where this is a smooth degree angular scale so that these fluctuations are sort of signal to noise or on the brightest level, signal noise of a few detections of the matter distribution on those angular scales. So now you can actually create maps of the matter distribution from the CMB, and you can use this to cross-correlate with weak lensing, shear surveys like from LSST to either improve cosmological constraints at some level or also provide a very powerful systematic check on any sort of systematic uncertainty from either measurement. So the next frontier for improving on lensing measurements of the CMB is really to move to polarization. And you can kind of see why that's true kind of simply from this plot. This is a plot of the temperature and polarization power spectra, autospectra. So lensing affects both the temperature power spectrum and B-mode spectrum by just smearing the power in the acoustic peaks. And it causes a relatively small change in the intrinsic unlensed power spectrum. But if you are able to measure the B-mode power spectrum, we don't expect any primordial B-mode signal except from inflation. And on scales about, certainly around 500 and above, the only lensing, only B-mode signal we expect is from lensing by large-scale structures. So if you're able to measure the B-mode power spectrum, you're getting a very clean measure of the structure on sort of at redshift 2 and with a very broad redshift kernel. So this is basically that same plot, now just plotted in log-log space, just showing this more explicitly. And so on large angular scales, the game is to try to measure this B-mode signal from inflationary, from gravity waves generated during inflation, where the amplitude of the signal is dependent on the tensor to scale ratio R and also the energy scale of inflation. And then once you get to around sort of 1 degree scales, lensing becomes the dominant, B-mode lensing becomes the dominant signal. And by measuring the amplitude of this curve, you can get a handle on the neutrino mass. So, Bill also showed this plot. This is sort of showing the current constraints on E-mode and B-mode power spectrum. Currently, we've measured the E-mode spectrum reasonably well already from several different experiments. But up till about a month ago, the B-modes had never been detected. And these are all upper limits from many different experiments. So this sort of leads into the project that I work on, South Pole Telescope. It's a 10-meter millimeter wavelength telescope at the South Pole. So this is about 5 times bigger than the Planck mirror, so it gives you about 5 times better angular resolution. And our main science channels are always going to be sort of centered around the peak in the CMB blackbody spectrum around 150 gigahertz. So we're observing 100, 150, 200 gigahertz, and that corresponds to sort of 1 and 1.5 arc minutes angular resolution. And so far, we've completed 3 surveys, there's 3 surveys either completed, the SPTSZ survey, underway right now, SPTpol, or planned, the 3rd generation camera, SPT3G, where we're going to use this telescope to better characterize small scale anisotropy and also the polarization, both in polarization and temperature. So just to give you an idea of what extra science you get by having this big telescope. On large, this is showing now a 50 square degree map from the full 2,500 square degree SPT survey. So this is about 7 by 7 degrees. All these large scale fluctuations that you're seeing are just primordial CMB anisotropy, the same that Planck and WMAP are detecting. But then the big beam buys you this extra resolution at smaller angular scales. Well, now you can start doing more astronomy, either detecting point sources, which typically are either AGN or pretty exciting high redshift, dust-obscured star-forming galaxies, which you can do follow-up with ALMA or other things like that. Or these shadows, these sort of characteristic shadows that you see in the CMB caused from clusters of galaxies, where the light from the CMB is distorted off this hot gas, and we can look for this shadow to find the most massive distance clusters in the universe. And up till pre-Planck, this shows what the best measurement of the CMB power spectrum was from combining WMAP, SPT, and ACT. So basically, SPT is always concentrated at L's above 1,000 or so, just because that's where we can improve upon the measurement from WMAP. And so we already had characterized this damping tail of the CMB, and then relative to Planck, we're actually going out to farther, smaller angular scales, higher L's. So around 2,000, we kind of pick up where Planck took off, and we're improving on the sensitivity and the constraints of the primordial CMB spectrum above L of 2,000, and out to L to 10,000, where other sources start dominating the microwave sky, secondary anisotropy from SZ effect and point sources. So beginning of last year, January 2012, we upgraded the SPT to be outfitted with the SPTpol camera. So this is now showing the 100 square degree maps from the first season of observations for SPTpol. These are the Q and U Stokes parameters maps. So we expect the CMB to have an intrinsic E-mode polarization sourced by these density fluctuations in the early universe. And what you're seeing here, the stripiness up and down on the Q map, and then diagonally in the U map are E-modes sourced in the early universe. So this is intrinsic primordial E-mode polarization that you can visibly see in the maps. I'm going to.
This conference is no longer being recorded.
All right. So I'm going to talk next about the results for the B-mode detection using this data. But just to say now that we've now moved on to a 500 square degree field, which we've chosen to overlap with the BICEP2 KEK experiments, so that this sort of high resolution detection of lensing, B-mode lensing that can happen with SPT can be teamed very powerfully with these large-scale experiments like BICEP2 and KEK to de-lens their data and principle improve constraints on the tensor to scalar ratio R. But those are still early days. So we use this 100 square degree map to detect the B-mode polarization. This is showing the SPTpol data. So this is on the left, this is the measurement of the E-mode polarization with that map from SPTpol. And we detected the B-mode polarization through a cross correlation. We're given this E-mode polarization that we measure, and then a measurement of what the expected lensing potential is, which in this case we used Herschel CIB measurements of these high redshift star-forming galaxies as tracers of that structure at redshift of 2. Using that prediction of the lensing potential from the Herschel CIB measurement, we can predict what we should see in B-modes with SPTpol. And we can cross-correlate that prediction with the actual SPTpol B-mode map to detect B-modes with much higher significance. And so this is showing now this cross-correlation of those two data sets, power versus angular scale. Black is the main result, which corresponds to a 7.5 sigma detection of lensing B-modes. The different colors just correspond to different systematic checks corresponding to different data combinations. Gray is a null test that we also performed. So you can see the nice thing about cross-correlation, it adds, it adds to the significance of the result, and then also many of the systematic uncertainties fall out in the cross-correlation. So it's a very clean, robust measurement of the B-mode polarization, albeit through cross-correlation. So what's next? CMB measurements have always been a sensitivity-limited measurement, and over the last 15 years or so, the push has really been to just ever more sensitive focal planes. We need to increase the detector counts more and more. And that's just because around 15 years ago, we started making detectors that were photon shot noise limited. And so the only way we can increase our sensitivity is just by making more detectors. And you can see that just looking at the history of focal planes over the last 10 years or so, going from state of the art 12 years ago was Akbar with 16 detectors to 1,000 detectors several years ago to sort of that level today as well, but now with polarization sensitivity. And in the future, we want to expand this more and more by orders of magnitude. And then I'm going to talk a little bit about this sort of future planned CMB stage 4 experiments next. So as part of this, sort of the SNOMAS process, the CMB community came together to sort of come up with a concept for the next generation stage 4 CMB experiments. And you can see that there's nothing that's fundamentally will limit us sensitivity-wise. We can still continue to make ever larger focal planes with ever more sensitivity. And this is just showing a plot of the sensitivity, instrument sensitivity versus year for ground-based measurements at various stages, which we defined in this process, were basically corresponding to order of magnitude increases in detectors, going from stage 1, stage 2, which is the current generation of system, stage 3, which is the next generation, we'll have 10,000 detectors, and then stage 4, which have 100,000 plus detectors. So, and then just for just to compare, you can also see WMAP and Planck on here where it compares. So today we're about here, and we just saw B-modes for the first time, but we want to go over to this lensing and inflationary science and measure at higher significance and start doing this additional neutrino and inflation science. And going out to CMBS4, you can project out, and we should be able to reasonably come up with a concept that has sort of an order of magnitude more sensitivity. And so for the CMBS4 mission, we basically came up with this concept where there would be a multi-platform experiment that would have 2 surveys, one designed to optimize for inflation constraints, which would target a few percent of the sky. A second survey should be a wider, shallower survey, mainly going after neutrino science, which would measure about half the sky. And to get the sensitivity required to start placing interesting constraints at the level we want, you need something on the order of a few 100,000 detectors. And they have to span something around between 40 and 240 gigahertz for foreground removal. And we need at least 3 arc-minute resolution to properly characterize the CMB lensing signal. And the approximate depth we're shooting for is something like 1 micro-K arc-minutes over half the sky, which is motivated by the science constraints I'm going to show you. And as I laid out, really the technical challenge in doing this was just the scaling up of these large detector arrays. So how good was CMB-S4 do in terms of inflationary constraints? Well, our goal was really this sigma R of 0.01 level, which is important because it's an important boundary for inflation, and if it corresponded to Planck scale, energy scale physics. And at R of 0.01, looking here on the left here, this is a plot now of the CMB power spectrum versus this multiple again. This top blue curve is R of 0.01. So at that level, you start running into lensing B-modes, start becoming a contaminant. Oh, thanks. And then foregrounds also become a problem. And this bottom brown curve here shows the foreground level for the best 1% of the sky. So you need to be able to clean foregrounds, and you need to be able to remove B-modes. But basically, in several concepts that we considered where we varied the beam size, the sensitivity, and sky coverage, you basically get down to run the 1e to the minus 3 level with many different experimental configurations. So this level, well, where we might detect R of 0.01 at 5 sigma, is pretty achievable over many configurations of a CMB-S4 experiment. In addition, CMB-S4 can start improve your neutrino constraints on the effective number of relative species in this large area survey. So I mentioned earlier that we're getting the constraints on NF from this damping scale in the temperature power spectrum. Well, you can do the same thing in the E-mode polarization power spectrum as well, where you're still measuring this damping scale, but you can go out to larger L, smaller angular scales, and get a larger lever arm because foreground contamination is less an issue at high L. And so this extra lever arm continues to improve the constraints on NF from the sort of plus minus 0.3 today, and gradually for our CMB stage 4 mission, you get down to NF of about 0.02. So now you can really make this precision test of the standard model prediction of NF of equal to 3.04, which is predicted from cosmology. In addition, you get ever higher detection of the CMB lensing potential. And at a level where now the relevant scale is we know neutrinos have at least a sum of neutrino masses of 58 MeV or higher just from neutrino oscillation experiments. So we want to get down to where we could detect something at a few sigma at that level of this sort of minimum sum of the neutrino masses. And for CMB-S4, this is showing now the joint constraints on NF versus neutrino mass, combining CMB stage 4 with a DESI BAO measurement. And also, you get down to this level of around 16 MeV constraints. So now you could detect neutrino mass, even at the minimum neutrino mass at a 3.5 sigma level. And this is also giving you a 0.02 constraint on NF. And so it's really exciting because in the very near future, we should be at the sensitivity with cosmological experiments where we should be able at the sensitivity where we can detect neutrino mass, even for the minimum neutrino mass hierarchy that we expect, this 58 MeV level. And we're going to have multiple probes that are going to be sensitive to this, measuring sensitive neutrino mass in different ways, CMB-S4 from gravitational lensing, DESI from both the BAO and redshift space distortions, and then LSST from a coarse weak lensing. And each gives around a 25, 30 MeV constraint on neutrino mass, and in combination gets you down to this sort of 15, 16 MeV level. And I'll just say else as well, so we heard a lot about clusters this morning. So this CMB-S4 experiment will also be a really impressive cluster survey. So this is now showing cluster mass versus redshift for comparing different SZ CMB measurements. Planck is in red. This is cluster mass versus redshift. Planck's in red. Black is SPT SZ. Blue is the expectation prediction for SPT3G. And then CMB-S4 should be below this 1e to the 14 level. So you should be at a depth where you will find 100,000 plus clusters extending out to very high redshifts from the shadow they make in the CMB. And with the sensitivity that we're achieving, you should be able to directly detect the lensing of the CMB from the individual clusters themselves, which is a very powerful tool to calibrate the cluster masses. And for SPT3G, we should get down to a level where you can constrain the cluster masses at the 3% level. And CMB-S4, you're doing really well. You're going to have many handles from both the polarization and temperature where you can get down to sort of a 0.1% mass constraint level. All right, so CMB is a very fundamental tool for cosmology. It gives you many handles on both early universe physics and also neutrino physics. And for this neutrino physics in particular, and ultimately for inflationary modes, going to small scales is critical because at some point you're going to run into this floor from the B-mode lensing component, which will sort of start limiting to you around R of 0.01. And so even with sort of reasonable projections from stage 3, stage 4 CMB experiments, we should be able to get these interesting levels of for R, NF, and neutrino mass, which for these latter two, we should see something and really be able to test standard model predictions for each of these observables. All right, thank you.
What's the difference in noise between the 4 iteration and the 3G? For the Y, the fourth generation Y and the
Right. So yeah, for stage 3 SPT3G, we're planning to get down to around 2 micro-K arc minute depth over 2,500 square degrees. For CMBS4, we're hoping to get half the sky down to about 1 micro-K arc minute. So it should be, roughly almost an order of magnitude more area, and then about a factor of 2 more depth for stage 4 versus stage 3.
A couple of questions. The first one, with regard to the survey that you're planning with the stage 4 experiment. Totally for the cluster stuff, you highlighted at the end it would be advantageous to have the 1 arc minute beam rather than the 8 arc minute beam. So
yeah.
what the cost penalty is.
Yeah. So I think, the 8 minute beam, I think, is probably out in the first place anyway, because we know we need about a 3 arc minute beam or smaller for detect CMB lensing effectively. And so probably we're at that range where it's going to be somewhere between 3 and 1 arc minutes sort of beam scale. I think in principle, either is possible. If you build a bigger telescope, you obviously have fewer of them, and if you build a smaller telescope, you want to have more to basically keep the throughput and sensitivity the same for a fixed amount of cost. I think there's still a decision to be made of what science is the trade-off going from 1 to 3 arc minutes, and both in science costs, risk, and actual costs. So, but even at the 3 arc minute level, you basically should have a fairly flat mass threshold out as I showed in that plot. And so the plot that I showed was actually for 3 arc minute beams, so you should only do better than that going to 1 arc minute, where the mass threshold sort of dips a little more going into higher redshift.